All right. So I wanted to try to reiterate basically the first half of the semester, and in particular the material that's going to be on the midterm. It's going to be Thursday in class. 4 questions, basically like, somewhat similar to the homework assignments you've been given. Maybe, not, but at the same time, you've got 25 minutes for each question, so there's a limit to how much I can ask. I would like most people to get most of the questions completely correct, because otherwise it takes us a long time to grade them. So hopefully, hopefully the questions will be, appropriately pitched. But, you will be expected to know, this material. So I'm going to cover 5, there's the broad outline of what we've done can sort of be put into 5 categories. That's skipping 1 or 2 things which are going to be brought up again in the second half. So okay, so it's not due yet, but you'll be expected to understand something about Lab 2, and you'll definitely be expected to understand the CPU from Lab 1. By understand, I don't mean that you'll be able to look at a binary instruction pattern and figure out which instruction it is. I have no idea myself until I look through that document. So the first half of the CPU homework, no, you're not going to have to do that. You're not going to have to remember all of the instructions. Any instructions, that are used in the exam will be listed there. But, given that information, you'll be able, you'll need to understand the concepts behind it so that you can take the information in the question and use it. And then, address translation and page faulting. A couple of logistical issues or comments before I get going. One is handwritten notes. Some of you have taken handwritten notes on a device. Please print them out, because there's no internet access while you're doing the exam. It's much easier to verify you're not accessing the internet on a piece of paper. If there are, reasons why it's more difficult for you to do handwritten notes than the typical student, please contact me and we'll work something out. I will point out this rule's been sort of developed, it's, you can have 100 pages of notes if you want. In general, it's not that useful to have 100 pages of handwritten notes. Although if you've got a notebook with, I'll take that back. If you have a notebook in order of how how the lectures went and so on, then in fact, a lot of times it's like, oh, that material was in, I forget which lecture, but it was about halfway back. Let's find it and search for it. It's, if it works together with your memory, then a bigger bunch of notes may be helpful. What I found with open book was people spent their time collecting information instead of studying it, and then during the exam they spent their time searching that information instead of thinking about the problem. Yes? Okay. Well, that's what I'm going to try and cover in this lecture, is what the particular aspects of this first half of the semester are going to show up on the exam, that you'll be responsible for on the exam. Yes? If it's handwritten on paper and you can carry it in with you and you can read it, then it works. That's, if you like tiny pages, you like huge pages, that's your own, if it's in a notebook, if it's, whatever. Okay. And then, you'll have, and then the exam, for the exam, I like to do assigned seating. Basically, I'm going to, when you come in here, you'll be asked to wait to sit down, and the exams will be face down with a sticker on the back with your name on it in alphabetical order by last name. So hopefully everyone can find their seat fairly quickly. So that just, that sort of equalizes everything. Basically, if someone else in the class has a, generally people copy off of friends who are willing to let them copy, and, your grade will be better compared to the class average if there aren't, a number of people doing that. It's, anything more complicated is too much, plus it's great having the stickers on the exams afterwards and knowing who didn't make it to the exam and stuff like that. All right, so we're not, there's a whole bunch of details about the C language which are, I would say, not really relevant to the material we're studying in this course. So, basically almost all the programming we're doing is going to be using integers. For the exam, I will tell you exactly how big an integer is. An array. And so on. That an array is just a bunch of items of identical size lined up in memory so that the compiler can generate code that calculates the address of entry I in this array by taking the beginning of the array and then multiplying I times the index I times the size of an entry, which also explains why, C, why indexes start at 0 when, in a math class, if you, actually by now they've probably changed this, but certainly, I was taught in math long ago that indexes begin with 1. This is why they begin with 0 in programming, because it's a nice, simple calculation. Okay, a variable in C has a name, usually a location and a value. The location is a memory address. And the value is whatever bits are in that memory address. That means a variable always has a value. If you have a pointer, it could be a null pointer. A null pointer is not a lack of value, it's a very specific value. On just about on any machine that I've programmed, a null pointer is represented by all 0 bits, and the and no valid, and there's never anything valid at that at the location corresponding to that. For a pointer, the value of a pointer is a location. So and the value of this variable p is the location of the variable x. This is some address in memory. This itself has an address in memory. Who knows what it has, this variable has a location in memory, and there's a value in that location. So an array is a bunch of values of the same type and same size consecutively in memory. You don't name the individual entries in the array. You address them with an index. And your code doesn't change if your array is 4 items long or 400 items long. The legal values for this index change, but you're still writing A sub I. A structure has a fixed size and different types of named fields. So let me in this case, we've got 4 different fields. A, B, str, and next. They can each have different sizes. And we access those fields by name. This is what's going on under the hood in Java or some other compiled language, Python does something else, which is vastly slower. But, you know, it's C++. This is how C++ objects work under the hood. You know, you have this lump of memory that's divided up into named fields. And then, you know, and typically in the software that I deal with, typically some of those named fields are pointers for lists, trees, other data structures. All right, so this is, you know, this is as much for the exam. You're not expected, you know, we're not going to ask you about syntax or library functions or something like that, but you should understand this concept that a variable has a location in memory and that it has a value, which are the bits in that location. And you should understand this concept of a structure. A structure is a template. It says, so an array is a very simple template. It says that if I have an array of 4-byte elements, then that has address A, then entry 0 is at A, entry 1 is at A plus 4, entry 2 is at A plus 8, and so on. A structure is a template saying that, you know, in this case, let's assume this is running on one of our, you know, running on our laptop, so on a 64-bit machine. If we, you know, if I ask this level of question on the exam, I might use the Lab 1 CPU instead with narrower pointers, but here we've got here this, oh, well, you know, if I have a structure of this type at address 1, 2, 3, 4, then that's going to be the same as the address of field A in the structure, because it's at the top of the structure. That address plus 2 is going to be P points to B, so here it would be 1, 2, 3, 6. You know, the next field is P plus 4, and the next one is P plus 12, which is, oh, I hate doing hex arithmetic in my head, so I won't. But, you know, in other words, this template, 2 bytes, 2 bytes, 8 bytes, 8 bytes, applies to any struct of this type. And so given a pointer to that struct, the compiler can emit code which will calculate the address of one of its fields You saw something like this as the last question in the CPU homework. So that's probably the key C programming idea I want to get across, is this, that structs are templates for a layout in memory. And so that's how we lump a bunch of fields into an object. Is, we don't link them together in a list, we don't put them in a dictionary, we allocate, in this case, a chunk of 20 bytes, and the first 2 bytes are going to be field A, the next 2 bytes are going to be B, the next 8 bytes are going to be this string, and so on, for this particular structure. In general, we rarely have to worry about the exact sizes of the fields in a structure, because the compiler is going to handle that for us. Yes? Is the 8 an arbitrary decision, you're saying? On most modern CPUs, on, I guess, any modern CPU, because something that can only address 4 gigabytes isn't very modern. On a modern CPU, these would be 4 bytes. They'd be 8 bytes. On smaller embedded systems or other things, they might be smaller. But that's, yes, and yes, and if I do something like that, I will make sure to specify what the width of a pointer is. Again, this is something that we normally don't, we normally just let the compiler do it for us. That's also why, if you change the order of fields in a structure, you in fact have a different structure, because the compiler doesn't know the names of these fields, or once the code is compiled, it doesn't know the names of these fields, it just knows the offsets. If we ever need the size of something in a code, in our code, we typically use the size of operator. Also, if you ever find yourself allocating 8 bytes, there's a good, you find yourself in a crash in the debugger and you allocated 8 bytes, there's a good chance that you allocated the wrong amount of memory because you were looking at the size of a pointer rather than the size of the thing that it pointed to. All right. So yes, here it's pretty obvious how big these 2 variables are. Here, you tend to know when you're working on a particular machine, but for purposes of asking you something, clearly I've got to specify exactly what it is. It's not. All right. So all right. So we'll deal with address translation separately from the CPU itself. In general, actually, could you just check that that green box is still showing? Okay. You know, for the most part, you can visualize address translation as this thing that happens just outside of the CPU in this memory management unit. So the CPU has some amount of state. It's got a program counter, it's got some registers, typically it has flags. You know, it's any CPU we want to think about has a stack pointer. And it has a very simple loop. You know, for that, your emulate function, you implemented one iteration of that loop. You know, if we were really emulating a CPU, we probably would have hoisted your code into the loop itself, because that would let the optimizer, you know, grab things better and make it faster, but it's much easier to test it the way that we did it. And really, it just does an instruction based on the state that's in the CPU at the time. You know, so we have instructions that we use for conditional statements and loops and so on, the conditional branches, and those just look at these flags, which got set in a prior instruction. You know, we have a function call and return, but those don't know anything about the function itself. They just push a return address on the stack or pop the return address and jump to it. So one thing to remember, because it may show up, for instance, it shows up in the page faulting homework, is that when you do a jump or a call or return, it changes the CPU state. If you do a jump, it changes the CPU state by setting the program counter, which will then determine where the next instruction gets fetched. It doesn't actually fetch an instruction from that location. It doesn't read that location. It doesn't do anything. It's just when that instruction finishes, the CPU, the next thing it will do when it fetches the next instruction is fetch from that location that was set by the jump instruction. Same thing for call, except that call also pushes a return address. And then a lot of the code that the compiler generates is manipulating addresses, because in general the code we write works with data structures. If we've got an address for this structure in a register or in a variable somewhere, and we want to access this field, we're going to have to add 12 to that address, because that's the offset in the structure for that particular field. In this particular case, that's a next pointer. So here we're going to have to add 12 to the address, read the contents of that address, and that becomes our new, and then store it to our variable here. If we were traversing a linked list, we might be doing that a bunch of times. If we were accessing items in an array, we'd be taking an address and we'd be multiplying an index by a size. Since our Lab 1 CPU doesn't have a multiply instruction, you might guess that we're not going to have an array example, and you'd be right. I think, I hope that folks are comfortable with the concept of a stack. That to push something, we decrement the stack pointer and then store. And then to pop something, we load and then we increment it. There's probably some, at least the CPUs we use do it in that order. And this gives us a very simple push down stack, which works as long as everything's the same size and the stack is big enough. But subject to those limitations, it's very simple, it's very fast, and so it's the perfect sort of thing to use for a CPU. Yes? Is a stack first in, last out? No, a stack is Uh, oh, yes, first in, last out. Yes, because if you think about it, you need that for function calls. When a function returns, you want to return to where that function was called, not to where the first function up at the top of the program, was called. So that first in, last out gives us the nesting behavior we need, because the depth first exploration of the call graph, essentially. All right. So before I go on, questions on C and on the CPU. Yes. Oh, how do you determine how much to push or decrement or increment the stack pointer? Well, you read the data book that tells you how much the CPU increments or decrements it. So if I ask you a question, I'll tell you. For lab 1, it was 2 bytes because we were pushing and popping 2-byte values, which made a lot of sense because addresses on that machine were 2 bytes. If you were to look at the code that the compiler generates on your virtual machine or on your Mac or Windows box, the stack on those machines pushes and pops 64-bit integers, 8 bytes, and so the stack pointer goes up and down by 8. If you want to push 1 byte onto the stack, well, you put that value in an 8-bit integer and an 8-byte integer, 64-bit integer, and you push it. You pop it back later, and you just take the bottom 1 byte. Like an array, it relies on everything being the same size. So yeah, I'll tell you. That's. Was there another question back there? You'll need to know how it works. Okay, I won't be asking a question about the whole stack frame, like local variables and function, and arguments and stuff like that. But we may have a question, for instance, like the page faulting one, where you might want to know sorry, the chalk is getting to me. Typically, I've reminded people of the semantics of push and pop when I ask a question using it. Because partly because this, whether you do, this is pre-decrement, post-increment, that's an arbitrary choice. So, other questions? All right. So, next we're going to talk about fork and file descriptors. This is actually relevant to Lab 2 as well. So if you think about it, well, so to start out, I mentioned early on this idea of, I/O virtualization, this idea that, the Unix API, system call API, lets you deal with a bunch of different things via this same read-write interface. And so the way it's implemented, well, um, now, if you imagine that you've got these totally different objects in, high-level objects inside the OS that each implement read and write methods. um, somewhere else we've got one that has our keyboard and frame buffer drivers, if we're, from the very beginning as well. Each of these is, an internal OS class that implements read and write methods, and it's got some amount of state. Like one of them is a network connection for SSH. One of them is something that pipes input and output over to the terminal application. If you open your VM, if you open the terminal app inside your VM. One of them's a pipe, which is just, a buffer that when you write into it, it puts characters into the buffer. And when you read from it, it pulls characters out of the buffer. Another is a file on disk. And we've got a file table that's associated with your process. That has pointers to some of these things. So maybe we've got a process that's reading its input from, the graphical terminal application, and it's writing its output to a pipe. And we probably have, another process somewhere that's reading its input from that same pipe. And, and it turns out we're going to need, well, I'll mention that, I'll put that off for a second. So this is how your application, unchanged, can write to all these different things. Because the write system call is basically going to say, is that file descriptor valid? Okay, if so, then call the write method of whatever it points to. And when you open something and when something gets created, when we open a file, for instance, we create a new one of these internal objects. When we start a new terminal, part of what it does is creates one of these new objects in the kernel. If you SSH to the machine, you have an internet connection in the kernel, a TCP connection. So your code doesn't need to know which of these things it is, because you just do the read system call, and the read system call doesn't need to know a lot about those details either. It just looks up the pointer, makes sure that everything's valid, looks up the pointer, and calls the write method or the read method. Now, what happens if we do a fork? Okay. So, in particular, this file table, it's per process, but it's in the operating system. If you were able to manipulate the pointers in that file table, you could do all sorts of horrible things. So instead, you just, your system call passes an index. The read or write system call verifies that the index is valid and looks up that object. If we do a fork, we copy the whole object, the whole process, which means the child inherits the file descriptors of the parent. Now, this means that we're going to need a reference count in here. This is a detail, don't worry about it. But and so, in particular, I wanted to explain something about the the second question on the file descriptor, the pipes and whatever homework, which is okay. So so what's going to happen is okay. So we've got at the top level, we've got two commands joined by a pipe. The first one of them is sh, and the second one is tr. And then when sh executes, it is just another instance of the shell. In this case, it's taking, instead of reading commands from from user input or reading them from a file if you were running a shell script, it's reading them from a command line argument. And so it executes so we had the two, we've got the parent, we've got two children, and then this one has two children. Now, sh was piped into tr, so the output of sh is going to a pipe. But in fact, that output is going to be generated by this second command here, which inherits the file descriptor. It's perfectly fine for multiple processes to be writing to or reading from the same file or the same pipe or the terminal. In general, it's confusing and probably not what you want if they're doing it at the same time. But if you think about it, in your shell, when you run a regular command, you're not closing standard in or standard out in the parent. Let's say I run ls. So when we started out, our shell was taking its input from and writing its output to the terminal. It did a fork and then executed our ls command. And this, when we did a fork, we inherited the same file descriptors. You know, we did a bit of, the kernel had to do a bit of reference counting magic to make sure that, you know, that once everything is exited, you know, that things get freed up once everyone's closed all of the file descriptors pointing to something, but we'll ignore that. So while ls is running, the shell isn't reading from the terminal. It isn't writing to the terminal. It's busy waiting for ls to finish. ls isn't reading from the terminal, but it sure is writing to the terminal. It writes its output, and then it exits. The shell finishes waiting, and then it takes its turn writing to the terminal again. You know, as I said, there's nothing that prevents you from having multiple things writing to the terminal. You can easily create a process that runs in the background and periodically prints things out, and it's very annoying. You know, similarly, you can easily have multiple processes trying to read from the terminal at the same time, or from a file at the same time. That's probably not what you want to do, because, you know, you don't know which process is going to get which line of input, for instance. But, you know, the operating system doesn't care. That's one of those things where, you know, it's perfectly legal, it's just dumb. So that's the thing, is that the way I/O is handled through fork and exec is through this idea of inheritance. And the reason because fork copies the parent process, including its operating system state, like, you know, open file descriptors. You know, it wouldn't be a lot of use. I mean, things like, you know, executing ls. It wouldn't be a lot of use running ls if it couldn't output its results to the terminal. It would be awfully complicated if you had to provide arguments to it saying, oh, you have to, you know, if there was an argument to ls saying, send your output to the third SSH connection on the machine, send your output to the second terminal window, or something like that. Instead, it just inherits whatever the parent shell was talking to, and it just writes to that output. Of course, if you redirect output or you pipe things, then the shell does some messing around, closing file descriptors, replacing them with other ones, and so on, to set up these pipes, to set up these output redirects, and so on. But that's, the key thing is that you normally start with input and output going to the terminal, and you and then those get copied when you do a fork. Speaking of which, for Lab 2, that's a strong argument for saying that you should do your output redirection inside the child instead of the parent, because if we redirect in the child, it can write to this file and then exit. Everything closes. We're all done. If we, once we're finished, if we redirect in the parent, then somehow we're going to have to, we're going to have to figure out a way to get back to our original configuration after that command ran. So in general, we want to leave the file descriptors themselves unchanged in the parent, and we want to redirect things in the child. One reason we left pipes out of this assignment to simplify it. They complicate things a fair amount because you've got to create the pipe in the parent, but then redirect in the child. Because obviously, I can't create the pipe in the child because inheritance goes one way. I can't create the pipe in the child and give it back to the parent and tell the parent to give it to the other child. Instead, the parent has to create it and give it to its children, and they then have to, redirect into it and out of it. And that logic ends up being a lot more complicated than just replacing standard in or standard out with a different file descriptor from a file you just opened. So questions, because this is a confusing concept. Yes? What are the chances that homework 3 will be graded before the exam? There's a decent, we're working on grading them. The solutions have been posted. I should have put a separate note because there's no notification when I do that. So solutions to to homeworks up through 4 have been posted. Solutions to 5 will be posted tomorrow morning, which means that if you submit it late, you're out of luck. The late day policy, the late policy for homeworks expires once we publish the solutions, and this is not, I think the most fair thing for everyone is to get those solutions out in time, before the exam. So tomorrow morning that'll get posted. And other questions? Yes. It will be significantly more specific than the, was it homework 3? As in, you know, I want to make sure that um, you know, but you should be, and also it is not going to include anything about file descriptor 3 and, you know, files being read or written that aren't redirected, because that complicates things significantly, and is also, the other thing is that it's, you know, sort of the bigger the text explanation block for a question, the more chances there are to miss something because of a dumb mistake. And that's, you know, on an exam that, you know, that's much more significant on an exam than on a lower point value, you know, homework that you've got days to look at. Yes. There's plenty that you ought to know, and, you know, for in general, but anything mentioned in the exam will be described. I don't think we're going to be able to get review problems up, but let's see. Okay, the previous time I tried to ask this question on the exam, I got it, I erred in making it too complicated. So this time I'm going to try and err on the side of making it too simple. So, but again, the key thing is understanding this idea of inheritance, and that you can think of file descriptors as they're just pointers in a table in the, you know, OS state for the process. They're a pointer to a thing somewhere in operating system memory. And so really what happens when we do a fork is we just copy that and we bump the reference counts. It's in the back. Yeah. That's a good question. I can talk to you about it later. Yes?
I was wondering if, so does each process have its own table?
Yes.
Okay, and then, because I wasn't sure, because, like, I think I read that, like, index, like, it's like a number that, like, points to, like, the actual, like, memory address of the file or whatever.
Okay, so think of it as there's this array, so there's per process state. You know, things like what's the current directory, you know, what's your user ID, what's some other things like that. And one of the things in the per process state is a table of pointers to, in Linux, it's a struct file that is, you know, so, but basically you have these objects which are, you know, all implement the standard file operations interface, and you have pointers in this table. So the table is private to the process. When you And that way, when you switch from one process to another, the read system call starts working on the table for the new process, because it just looks up current process descriptor, file descriptor table, index I. The things that those tables point to can be shared. Well, can be shared by, no, not globally. The sharing is very specific. The way that it can be shared is through inheritance. So when I fork, I make a copy of that table, and it has pointers to the same operating system objects that that the parent did. So if I had an SSH connection as my input and output, so there's a TCP connection in the kernel, the parent is going to have pointers in its table for standard in and standard out, for 0 and 1, pointing to, some object in the kernel, in the operating system, corresponding to that network connection. And then when I do a fork, we're going to copy the file descriptor table, and that new file descriptor table is going to have pointers to that same network connection. Now, if I open a file descriptor to a particular file in that child, I'll have a pointer to some other object, and that'll be private to that child, because that's unless that child does another fork. So that's the thing, is that the only way that open files go from one process to another is by inheritance. And the inheritance works because of the process copy semantics in fork. That after you do fork, the child sees the same memory layout, it returns to the same, the child sees everything the same except for the return value from fork. And so that includes open file descriptors.
Is this copy on write for the file controls?
No, it doesn't usually. It doesn't bother doing that. It does copy and write for like all the process, the address space that your process sees, but this typically, I think on Linux, this has a max of 1024 entries, and usually it's a lot smaller, and it keeps track of how many are valid, so it doesn't have to copy any. So it just copies it. Other questions? Yes. Mm-hmm.
Yeah. What ends up being the return? Like what?
So basically, so when you call into fork, the OS makes a copy of the process, and then it returns in the parent and gives you the process ID of the child, which you need in the shell because you're going to wait until the child finishes running. And it has to return from fork in the child, because how can it start running your code otherwise? And it flags that case by returning 0. So process IDs are never 0. And 0 is in the child. And so at the moment that you return from fork, the only difference between the parent and the child is that return value. And so that implies this whole, inheritance that, if you do a write to standard out as the next line in the child, it will do the same thing as it would do if you did a write to standard out in the parent. If they both start doing that, you'll probably get gibberish on the screen, but, typically, for the shell, for instance, because of the way it works, it makes sense. The child uses the output while it's running, and the parent waits. And then the parent uses the output again to prompt the user for another command, and so on. But yes, that's the being in the child is signaled by a 0 return from fork. Being in the parent is signaled by getting a valid process ID as the return value. All right. So I'm going to quickly, well, I've got 10 minutes left. So for address translation, it's just a matter of the MMU translates virtual addresses to physical addresses by translating the virtual page number to the physical page number using the page table. Okay, so we split the page number up into 2 parts. We index into the top level with one part, and we index into the bottom level with the other part. And that gives us a page number. Well, it gives us a present bit saying whether it's valid or not. And it gives us a page number, which is the actual translation. So So the key thing about a page fault is that when the OS returns from a page fault, the instruction gets retried. So typically what we do is, so what the OS does is it fixes the page table and then returns. In particular, a lot of instruction, every instruction has an instruction fetch. You've got to fetch the instruction from memory. That's a memory access. That might fault. Some instructions have either load from or store to memory. Oh. There's load and store. The other instructions that access memory are push and pop and call and return. Call and return access the stack in the same way that push and pop do. Remember, okay, so in particular, this instruction is there's going to be a memory address for a fetch, and there's going to be a memory address to an address on the stack, but we're not going to touch the address that we're calling. We're just going to set the program counter. And that doesn't involve reading from memory. That instruction just succeeds. And then if it's, the next instruction might fault because the next instruction is going to get fetched from 2000, but the call instruction is perfectly happy. And then finally, the varieties of faulting we talked about. Demand allocate, demand load, and copy on write, which is too complicated to put on an exam question. All right, that's all. We will see you on Thursday.